Okie dokie artichokes. It is me, Mr. Rebuff. We are in our final approach to the AP Stat exam. So here we go. We're going to go through some common errors, also some kind of reminders of how to say things that are pretty easily mixed up is a really good way to review kind of as we're approaching the final. So for univariate graphs, we are pretty good at this by now. So socks. But don't forget to add the context, right? If they ask you to describe a distribution at some point, as you're talking about shape or outliers or center or spread, say what the variable is, right? Say height, or, for this one, right? So the height, the average height, or the mean height is, right? So adding that context in at some point as you go through the socks is key. If you are graphing your own, if you are sketching the graph, if you sketch the graph, don't forget to label the variables. And we also need to get the numbers on the graph, right? So we know the scale. Okay. So make sure we have those. Final little piece of advice when we talk about skew is a shape in AP Stat. I know in like regular parlance in the English language, we would say, oh, this skews the data. This skews the data. We don't use that in AP Stat. So do not say the outlier skews the data. Yeah, or the outlier skews the mean. Don't say that. Skew is a shape. Okay. Comparing univariate graphs. Here we go. Be explicit. Okay. So if they ask you to compare this to this, or they have two box plots or two histograms, again, we will use socks, but you must explicitly compare them. So let's say I'm talking about spread. Spread looks fairly similar. So it's similar. Before and after are similar. Or I might say outliers. Let's go center here. Maybe the mean or the median for before is higher than after. So I would say that median is higher for before than after, right? I am explicitly comparing. I would not just list the socks for this and list the socks for this. I want to compare the shapes. I want to compare outliers. I want to compare all of those things. Okie dokies? Okie dokies. All right. Box plots cannot show that a distribution is approximately normal. So if you get a box plot or if you graph a box plot that looks like this, right? And it looks, oh, wow, that looks great, right? It could have come from a distribution that looks something like this, right? This distribution right here, this histogram could yield, if I did a box plot of the data, could yield something like this. This is definitely not normal, right? This is uniform. This is a uniform or uniform-ish shape, fairly uniform. Okay. So when we talk about box plots, never use the word normal. Okay. So when we talk about box plots, talk about symmetry. Symmetry or skew or lack of skew. Remember, skew is a shape, right? So if I see something like this, I might say that it is skewed to the left. Skew left. Right? If I see something like this, I might say it's fairly symmetrical. Fairly symmetric. Okay. But we would never, ever, ever say approximately normal. Don't say normal for box plots. Cool. All right. Speaking of normal, normal CDF. Normal CDF. I know there's a normal PDF on your calculator. It is never PDF for normal. We never, ever use normal PDF. It's always accumulation. Okay. My advice is this: make a sketch and always show what your calculator entry was. Mystery of skull score is normally distributed, mean of 100, standard deviation of 10. As soon as I read that, I'm drawing a normal curve. I'm going to put 100 right smack dab in the middle. I'm going to show my standard deviation is equal to 10. Okay. What is the probability that he gets a 90 or less? So I'm going to do something like this, 90 or less. This makes it really easy to show my calculator entry, right? Normal, CDF, and then the low value. You could use 0, or you could use a big negative number, an approximation of negative infinity, but 0 is far enough away that that would be fine. My right endpoint, and then the mean, and then the standard deviation. Plug that in, press enter, and you're good. Okay, so there's normal CDF. Boom, we're moving right along. It's going to be fast. Describe a scatter plot. Okay, so there's no socks for this. I need to come up with a good one for this. But a good idea, just as you're looking at it, draw something through it. If it's linear, it's going like this, right? This is looking like something like this, right? If I did try to fit a least square regression line, it wouldn't be very good, right? So for this one, we are going to talk about direction, form, strength, and put it in context. Oh, any outliers or influential points. And then we're going to put it in context at some point, right? So this is I would say, if we look at it as a non-linear, I'd say it's a moderate non-linear. So there's my strength. Oh, I got my strength form, positive relationship. And now I do the context between age and I can't even see what it says. Age and jawbone, something like that. Length. And then I would talk about outliers. I don't see no stunning outliers in there, right? So that's describing a scatter plot. Strength, direction, form, anything outlier, influential, clusters, anything weird that you notice. Are there big gaps? So anything weird, not just outliers. And then definitely get in the context. When we talk about context, we are talking about the variables, your X variable and your Y variable. Make sure you have that in there when you describe it. All right, here's the big one, right? Describing reading computer output for linear regression analysis, right? Here's one thing that I see some of you doing on your tests. This is smart. Okay, so this is your Y intercept, right? Your constant. This, therefore, would be your slope. Okay, this is your coefficient of your slope. This is the coefficient of your y-intercept. So let's go down here. Equation of least square regression line. Don't forget your hat. Okay, it's a predicted line. This tells us that it is predicted. So when if they ask you to create an equation for a least square regression line, don't forget this or the word predicted in front of it. So y predicted is equal to 0.2457x plus 147.1427. Okay, so my slope and my intercept. Okay, got it. Easy peasy, easy peasy. It's usually a good idea to say what X is and what Y is. I don't know what it is. Oh, it's sodium and something maybe. So X is amount of sodium. And maybe this is probability of hypertension. Who knows? Hypertension or something like that. Who knows? I'm making that up right there. You would need to look through the problem to see what Y represents. Okay, actually, probability, that's more than 100%. So I don't know what it would be. Hypertension, blood pressure or something. Let's call that that. Let's call it blood pressure. Okay. Cool. Finding R from R squared. So I look up here and I see R squared. So step number one, square root it, 0.5423 equals blah. Now, is it plus or minus? Is it positive or negative? I could look at the graph or I could check the slope. Slope is positive, so it is going to be positive. So slope is positive, so it is going to be positive. Okay. If our slope was negative or we saw a graph and it was going down as we went from left to right, we would be able to change it. Remember, R squared will always be positive. R can be positive or negative. R is the coefficient of correlation. It tells us strength and it tells us direction. It doesn't necessarily tell us if it's a linear relationship or not, So we don't say that R tells us that it's a strong linear relationship. R can tell us how strong the relationship is or the direction. So direction is either positive or negative. Strength is either strong. That's when it's like 0.9 and above, or negative 0.9 to -1. It can be moderate or it can be weak. And you can use some fudge words in there, right? Moderately weak, somewhat weak, fairly weak, extremely weak, right? Cool. R square is the coefficient of determination. Okay. Oops. Scroll down here. It tells us the percent, um, um, the percent. So for instance, here, 54% of the change in whatever my y variable is explained by a linear relationship with my x variable. Okay. So 54% of the change in high blood pressure or blood pressure is explained by a linear relationship with sodium intake. Okay. So R square, I always think that square means those two little circles, right? So squared is this and this. R squared is the percentage. Okay. Interpreting slope and intercept. Use the word predicted. And don't forget to add context, right? For every increase of 1 sodium, we predict 0.2457 more higher blood pressure, right? If somebody has 0 sodium in the diet, right, we would predict, right, my y-intercept, 1.47 blood pressure of that. Cool. So don't forget the word predicted and don't forget to add the context. Okay. All right. Is a linear model appropriate? Look at the residuals, right? What we want to see is kind of random scatter about the least square regression. Okay. Some bad things in the residuals, right? Okay, remember this was on the final. We have something like this, a situation where increasing variability. That's bad. We don't want that. We want it to stay even. We want that variability to stay even. We should not have a pattern in the residuals, right? Pattern is bad. Okay? We don't want a pattern in the residuals. And then the final thing we don't want is like a whole bunch like up here and a whole bunch down here, right? This is not normally distributed. Not normally distributed. And by this, we're not talking about this way, side by side like this. We're talking about this way, right? Where more of the stuff tends to be close to the line and less as you go away from that, y equals 0 line, right? Cool. We want random scattering. That's the goal. When we don't see it, there's a problem. All right. There we go. Moving on. Using a table of random digits, Mr. Rebuff has 26 identical pink socks, 51 identical blue socks. He picks socks randomly from his drawer until he finds 2 pink ones. Obviously I'm just pulling and pulling, no replacement, right? Good question if you're thinking that. Use a simulation to estimate the number of socks picked until he gets a pair of pink socks. All right. So when we do this, we have to talk about how we're going to use this. Okay. Pretty common. Once out of every like 5 or 6 tests will have this, it seems, on average. So how many digits at a time? I'm doing 2 digits at a time. Okay. What do they represent? 26 pink ones. So 0, 1 to 26. Don't forget that, right? We're doing 2 digits at a time. So I need to show 2 digits there. Will represent pink. And then 27 to, I think, 77 will be blue, right? What am I ignoring? I'm ignoring 00. I'm ignoring 78, I guess, to 99. Ignore. What about repeats? I'm going to ignore repeats. If I said I was putting the socks back in, that'd be silly. But sometimes we do. So we are going to ignore repeats. Got to talk about how we're going to treat them. We're going to stop when we have 2 pink. And then what are we counting? Number of socks. Number of socks until 2 pink, right? Down below, I'm going to do it. There we go. 27 is blue. 79 is ignored. 81 is ignored. 25 is pink. Yay. 11 is pink. Boom. Right? So we have a blue, a pink, a pink. We ignored these. So this is 3 socks. That's what I'm counting. And I would continue that a couple times. And usually they'll say, do it 3 times and find the average. Right? Pretty common. All right. Explaining confounding, right? So a new drug and how does it affect people who suffer from diabetes, right? If I'm concerned that age is a factor in diabetes, age could be a confounding variable. And the way I talk about it is important, right? I need to talk about how it could be confounding rather than just saying age could be a confounding variable. So I'd say something like this. Perhaps younger people are more likely to eat well, exercise. You can choose exercise, which what could it do? Reduce level of diabetes or chance of getting diabetes, right? Thus, age and drug type may not be distinguishable with regards to their effect on diabetes. So I don't know if it's this or this that's causing that. So what should we do? We should probably block, right? Yay, blocking. Blocking. I'm gonna get my notes, make sure I'm getting everything right here. Always block similar. Always, I'll try again. Always, I'm trying to go fast. Block similar. Okay, similar. Always block similar. And then we must randomly assign, so random assignment within each block. Okay, we had a problem on our final exam. It was kind of like this. This one I've seen before too, where we have like 16 plots, right? And there's a river here, and there's a forest here, or maybe there's a, I don't know, river here. There's a desert here, right? We're growing plants and we see which ones grow the most, right? Obviously, closer to the river is better than closer to desert. So how would I block? I would block here and here and here and here. So this would be block 1, block 2, block 3. And then within each one, maybe there's 2 different types of trees that I'm growing, right? I would randomly assign the 2 treatments to these 4 groups. So we have 2 new trees and 2 old trees. And I do that within every block. That way, we make sure that the river and the desert have the same amount of effect on each of the 2 types, right? That we're doing in there. Cool. Cool. Let's see, anything else on blocking? Nope, we're good. All right, match pairs, match pairs, match pairs. We have 2 options for match pairs test. Match pairs, we find the difference within each pair, and this turns into a paired t-test, right? Okay, so something to look out for. Same experimental unit. So if the experimental unit is doing something twice, they will do treatment 1, treatment 2, but what do we need to do? Randomize which is first, right? Randomize which goes first. Okay. We could also have 2 similar experimental units, 2 people who are similar ages, 2 people who are similar heights or something, whatever it is, 2 people with experience levels that are the same. They must be similar. Match pairs is a type of blocking, but we would then randomize which gets which treatment. Okay. So there has to be some randomization within the pairs. Okay. And I said experimental unit. A lot of times that's a person, but it could be a couple of different trees. It could be 2 seals. It could be whatever. Right. All right. Here we go. Stratified versus blocking. They're similar ideas. They're similar. Okay. They both of these separate into groups that are similar within. Oops, sorry, you can't see that. Okay, so both stratified and blocking separate something into groups that are similar, right? Stratified is for surveys, though. Okay, so if I'm asking prior year students what their favorite lunch is, and I want to make sure I get freshmen, sophomore, junior, and seniors in it, I would stratify that sample. So this is a sample, right? So sampling method, usually done with surveys, right? Blocking is for experiments, okay? And we block because we are afraid of confounding variables. I would block by age. I would block by distance to the river. Okay. So they're similar in that we're separating them into similar groups, all the freshmen, all the sophomores, all the juniors, all the seniors. Okay. But one is for sampling, just grabbing a sample from a population. The other is we're blocking when we do an experiment. Okay. Um, Speaking of experiments, generally use volunteers. A lot of people were like, what's wrong with it? There's a question, I forgot an exam at some point, and people are like, no, you can't have volunteers. No, almost every experiment that's ever been done uses volunteers. The only exceptions are like not good exceptions, right? People like doing research on inmates and that kind of stuff, right? Without their knowledge of it, right? That's not okay. Those are not volunteers. So experiments generally use volunteers. That's not a problem. So stop thinking that is a problem. Completely randomized design, right? All right, let's talk about this. Volunteers going into two groups, say what the treatments are. So group one, group two, define what treatment one and treatment two are. And then at the very end, do not say compare results, compare specific. So be specific about what we're comparing. It's usually in the question itself. Compare diabetes level, compare, I don't know, what is our thing on number of jump shots made, right? Whatever you're comparing, be specific about what you're comparing. Okay. Describe treatments here. Describe treatments. Treatments, right? So describe treatment here and here. Maybe this group gets training by Coach Mosley. This group gets training by Mr. Reboff, and we're going to compare who can make layups better, right? We need to have random assignment to the two groups. This is not an SRS. Simple random samples take a population of interest and take a sample of that, right? This is not it. We have volunteers and we're just separating them into the two groups. We're assigning them randomly into the two groups. So this is random assignment, not a simple random sample. Do not write simple random sample. You will lose points. Okay. Good idea to describe. Put all names into a hat, right? The traditional one. Okay. That's not always a point on it, but it's often enough that you should do that. All right, next one. Probability is always between 0 and 1. Okay, so if your calculator spits this out, right, that does not mean the probability is 2.2. Okay, 2.23, blah, blah, blah. E to the negative 7 means times 10 to the negative 7th power, right? 2.23 times 10 to the negative 7th would be like 0.000000223. I might have one zero too many. I'm not going to check. Okay. But that's what this means. That's between 0 and 1. Okay. If you see e to the negative 7, that's a small probability, right? So anytime it looks like your probability is more than 1, it's actually really, really small. It's close to 0. All right. Never, ever, ever commit. Okay. We've talked about this before. Never say the word proves. Never say the word true. Never say the word except. Okay. We never commit fully. Instead, say things like there's significant evidence of blah, 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 right? My advice is to always use the question to guide your answer, right? The question might be, is there significant evidence that this happens? And you would say, yes, there is significant evidence that this happens. Straight up copy it, right? Plagiarism is 100% acceptable on the AP exam, makes it easier to grade, makes it easier for you to write. 100% go for it. All right. 18, conditional probability. Find probability of male given blue. This is on your green sheet. You can find it. Look for it right now. I don't know if your green sheet will be green. It might be just white. Who knows what color it'll be? But you'll see conditional probability looks something like this. A given B is equal to probability of A and B divided by probability of B. Okay, so that is on your sheet, probability of A and B happening. So male and blue is right there. So that's going to go on top over the probability of B. That's blue. So this is A, this is B. Over the probability of blue, blue is 30 yeah, oh, out of 30, right? So there's 30 blue. There we go. So 10 out of 30. If you did the probability of A and B, you'd have to find out the full number here. I think it was 30, 40, 50. Is that right? 40 and 50. I think this is 90. So you could do 10 out of 90 over 30 out of 90, but you see that the 90s cancel out. It ends up being just 10 out of 30. So probably a male given blue. There's 30 total people who chose blue. 10 of the 30 are male. There we go. There's probability. Okay, cool. But look for the words, look for the words given that, right? Whenever you see given that, open your green sheet and find that right there. All right, linear transformation on statistics. On a recent test, the average score was a 35. Standard deviation was 5. Mr. Rebuff, being a nice guy, says, hey, I'm going to curve this, even though it's not a curve, it's a linear transformation. I'm going to multiply each score by 2, and then I'm going to add 10. What happens to the mean score? Well, the mean score is going to get affected by both of these, right? The mean score is going to go 35 times 2 plus 10. We've got a new mean score, right? Everybody's score is going up. But the standard deviation is going to change only by which one? Only by the multiplying, right? Only 5 times 2. Okay, it's not going to be affected by this, right? Remember, you can always like draw a picture of it. If I add the same thing to everything in this distribution, it just moves over. It's the same, um, same standard deviation, same range, same IQR, right? That stays the same. So just a real quick reminder, multiplication and division will change both center and spread, but addition and subtraction will change only center. It will not change spread. Okie dokes. Cool. All right, here we go. Moving along, moving along, moving along. Combining variables. All right, Mrs. Rebuff and Mr. Rebuff run a marathon, right? Mrs. Rebuff, this is her time, this is her standard deviation. So her average time, her standard deviation, and my average time and my average standard deviation. If we run back to back, how long would it take? All right. What would the combined distribution look like of Mr. Rebuff, right? So the mean of combined would be 4.3, 4.3 plus 5.3, right? I think is 9.6. The standard deviation, though, we cannot add standard deviations. We have to turn them into variances, and that's by squaring them. Then we can add them together, but now it's just variance, so we have to square root them, okay? So change it into variances, add them together, square root it to get it back in. Okay, so what about the difference? And let's go Mr. minus Mrs., right? So how's on average, how much slower am I than her, right? So we take 5.3, the mean of the difference would be 5.3 minus 4.3. That means she usually beats me by 1 hour, right? I guess I could put hours here. The standard deviation of the difference is going to be exactly the same as what's up here. Okay, even though we're subtracting, we still always add. Okay, if we subtracted, we would have 0. That would mean she always beats me by 1 hour, and that's not true. I mean, she usually does, but sometimes it's only by 40 minutes, right? Cool. When you have these mean and standard deviations, they sometimes ask a follow-up question. Because you have the mean and the standard deviation, you can now use normal CDF. What is the probability Mr. Rebuff actually beats Mrs. Rebuff, right? Normal CDF, negative infinity to 0, because that would be me beating her is negative numbers, right? Positive numbers is I'm slower than her. And then the mean and then the standard deviation. Cool, cool. All right, mean and standard deviation of a discrete distribution. We just had this on a practice one. To find the mean of it or the expected value. They like to use that word a lot. Expected value, right? We multiply down, multiply down, multiply down, and then we add across. Okay, so this would be 2.5, this would be 1, this would be -2. So I think we have the expected value would be, is it 1.5? 1.5. Okay, whatever that means. I don't have any context here. All right, to find the standard deviation, I believe there's a formula for it on your green sheet. Let's grab our green sheet here. Let's see, where is it? Where is it? Where is it? I know it's on here somewhere. Right here. There we go. So discrete random variable x, there's what we just did to find the expected value. This is it, right? We take the mean, we subtract it from the outputs, right? Or each individual output. We square that, and then we multiply by the probability, and then we square root it. So for the standard deviation of this one, I'll just start it over here just so we can see it, right? I'm going to take, oops, sorry, standard deviation is equal to big square root. I'm going to go 5 minus the mean. So 5 minus 1.5. I'm going to square that, and then I'm going to multiply the probability, 0.5. Then I'm going to add the next one, 10 minus 1.5. 10 minus 1.5. And I'm going to square that, multiply by its probability, right? So I'm going to do that for all three of them. I know I kind of ran out of room. I should have given myself a little room here. And then this one's -5 minus 1.5 squared times the probability of that one, 0.4. I add those together on the inside. I square root it. Not likely to see this, but you can. But the formula is there for you. Okay, so the formula for both of those are there, right there, smack dab in the middle of this piece of paper. It's probably the top of paper in your thing since I combined some of this stuff. All right, good stuff. Binomial versus geometric, PDF versus CDF. Okay, so binomial is a set number of trials, right? Shoot 10 3-pointers. Okay. Geometric is tries until first success. Okay. Shoot till first 3-pointer. How many shots does it take? Okay. That is geometric. It could take forever. Yeah, I could get success on the first one. Who knows? Binomial, I am shooting 10 and saying how many I make. Okay. PDF is exactly one outcome. Okay. What's the probability that Mr. Reboff makes 7 out of 10 3-pointers? What's the probability that his first success is his third attempt? That's geometric PDF. Okay. CDF is an accumulation from the left. Okay. And the left can be 0 for binomial or 1 for geometric. We can't have 0 for geometric, right? Because I could have my first success on my first try, right? I can't have my first success on my 0th try, but I can make 0 free throws out of 10. Okay. So PDF and CDF. Let's see, is there anything else here? Oh, if they say the words at least, and you have an older calculator, you might go 1 minus the CDF, right? 1 minus the CDF, right? And be careful of your cutoff, right? Be careful of your cutoffs on these. All right, population versus standard deviation. Let's see, right here, sampling distributions. All right, so population versus sampling distribution. So if a mean, let's draw a little population. If mean has a population distribution that looks like this, right? It's definitely skewed to the right. There we go. So a lot of stuff on the higher end, less here. My sampling distribution, if let's say n equals 4, would start looking a little bit more normal. Okay, it might look something like this. Okay, where it goes like this, something like that. My sampling distribution at like n equals 25 is going to start getting fairly normal. It might have a little bit of skew still left in it, but it's starting to get more and more normal. So as sample size gets bigger, as n increases, we become more normally distributed, more normal, less variable. Okay, my standard deviation is the standard deviation divided by the square root of n. Okay, so that's less variability for means. And then let's see. Oh, the mean stays the mean. Mean stays the mean. So if the mean score was 80 here, the mean score is 80 here, the mean score is 80 here. It stays the same for all of them. Okay, but you can see we're getting less variable and more normal as the sample size increases, right? For proportions, the population, this is kind of weird because it's either like yes or no, right? So if it's, I don't know, percent of people who think Miss Rebuff would look better with hair. Um, and so this is 0, this is 1, and let's say this is 80%, 20%. Okay, so that's the population distribution. If we had a sample size of 1, right, and equals 1, we just ask somebody yes or no. They either say yes or they say no. There's only 2 outcomes here. But if my sample size was 4, I could have 2 people say yes and 2 people say no, or 3 people say yes and 3 people say no, right? So we're going to get something that looks a little more distributed, maybe like this, right? Okay. But that is looking a little bit more normal, right? If I get to n equals 25, I ask 25 people, right? Hey, does Miss Rebuff look better bald, right? We're probably getting something that's looking a lot more normal. Maybe it's not totally normal yet, but it's starting to look even more normal than before and less variable. Okay, so same thing happens here. As sample size increases, we become more normal, we become less variable. For these, for the standard deviation of this, we would get root p 1 minus p over n. These are both in your on your green sheet, right? We've seen it many times. The mean stays the mean. So the mean of our x bars here is the mean of the population. The mean of our sample proportions is equal to pi, whatever that is. So this should be centered at, I guess, 20% success, right? So 20%, this should be centered at about 20%, right? So we stay centered at 20%, okay? If 20% say yes and 80% say no, the mean is 20%, right? Okay. Interpreting confidence intervals. Okay, we are 90, let's say 95%, could change, right? It's not always 95% confident that the true, right? The true, blah, use your parameter here, is between blah and blah. Okay, always have your context in there. Context is important. So that's interpreting the interval itself. This is your interval, low end, high end. And this has to be your parameter. It's not the sample. We know the sample mean is inside that interval. We know the sample proportion is inside that interval. It's smack dab in the middle of the interval, right? What we're looking for is the population mean or the population proportion in the middle of that thing. Okay, so that's the key there. Confidence level means this, right? If we're describe what 95% confidence means. Okay, so you say something like in the long run, 95 out of 100 confidence intervals created would capture the true population, whatever, mean, proportion, whatever it is. Okay, this is parameter. Okay, and be specific about it. Cool. There we go. All right. Last page. Kind of fast-ish. Yes. All right. Let's see. All right. Assumptions and conditions for inference. If in the prompt it says assume conditions are met, just say stated and then draw an arrow to it. You don't have to relist them at all. Don't take time doing that. If it says this, when you get to fat pi and you're doing your A, just say stated, draw an arrow, circle it, you're done. Okie dokie. If it doesn't say it, these are the ones that you always check. Random, because we want a representative sample, and this helps us attain that, right? We have independence, which is our 10n less than the population. Okay, our sample size cannot be too big, right? Or the population needs to be big enough to support our sample size. Okay. Um, Nearly normal changes based on what we're doing. Okay. If it's proportions, nearly normal is going to be my n times my p, and n times 1 minus p need to be greater than 10. Okay. If it's two samples, it would be both n1 p1, n2 p2, and n1 1 minus p1, and 2 1 minus p2 are all greater than 10, right? Obviously. All right. If it's means, we've got multiple things that can happen. So number one, we're looking for, is it stated? Is it stated? Sometimes it'll state, assume the population is fairly normally distributed. If it's stated as such, distributed, then you're fine. You could say, hey, it's stated up above. That's great. That clears it. Is the sample size greater than 30? If it's greater than 30, we're all good. We can just say, hey, sample size is greater than 30. Remember, we talked before about how when sample size increases, sampling distribution becomes more and more normal, right? Once we get to about 30, even the weirdest, funkiest population distribution, sampling distribution is going to look pretty nice. If neither of these work, we need to look at the graph, right? So we need to look at the graph. We either need to create it or we need to draw one, right? So if it's already there or we have to draw it, we are looking for, does it look fairly normal? And I would stick to things like, is it symmetric? Is there not much skew? Not much skew. Those are the things we're looking for. If it's on the AP exam, it's probably going to be just fine. Okay, so if they have a graph, if it's if they give, we're looking for those two things. If we have to draw your own, because they give the data, that happens a lot. Draw your own. You can choose what it is. I like to use box plots. I think they're the easiest, but again, we can't say normal. We talked about that before, but we can say the box plot created looks fairly normal. Make sure you label the box plot. Okay. Don't forget your labels on this. Don't forget to, do that. So make sure you label your graphs if you do that. Okie dokies. Okie dokie. Means can be two sample as well. If they are, both N1 and N2 must be greater than 30, right? We could look at both graphs, that kind of stuff. Let's see, what else do we got? If two sample, if linear regression, oh, shoot, one more thing for two sample, my bad. So if two sample just changes, the nearly normal changes, that's up there. If two sample, we also have to have independence between the two groups. Okay, that's a new one. Okay, so this is important. We have to add the independence between two groups, right? If there's not independence, we're probably doing a matched pairs, right? If it's linear regression, we need to check liner, right? And this is randomness. This is independence. This is, does it look linear? Does it look linear? Right? So that's just like, look at the graph. Does it look kind of linear? Yeah, it looks linear enough. Let's go. It will always do that on the AP exam. And then the N and the E, you have to look at the resids. Okay. Look at the resids. And what we're looking for is that they are normally and evenly distributed. We talked before about what just what resids look like. We're looking for something randomly scattered around the line. It stays pretty even as you go from left to right. It's not increasing or decreasing in variability. There's no patterns, that kind of stuff, right? Are our resids looking good? Okay, you got to check that. All right, here we go. One-sided versus two-sided. Tests. Draw a picture is the hint. Oh yeah. So let's say I think I had an example. Um, I don't know. Thought I had an example. So let's say a distribution. Oh, let's just use Mr. Rebuff's one. So Mr. Rebuff's was hint draw pick, right? So Mr. Rebuff um, golfs and his average score is 100 with a standard deviation of 10 and he hits a 92. So he hits a 92. That's right here, right? If it's a one-sided test, less than, so if my null hypothesis is my mean is less than 92, right? I would look at this. If it's less than, I'm doing this probability. I could do greater than, right? If I did greater than in this situation, um, boom, great. What's the probability if my null hypothesis was greater than 92? Oops, sorry. This would be null hypothesis would be greater than 100, right? Um, greater than 100. Would look something like this, right? If it was my null hypothesis is the mean is not equal to 100, then I have a two-sided test, right? At 92. And then I'm going to find that same distance here. That would be 108, right? And above. Okay, so one and two sample tests kind of depends if you're greater than or less than, which way you go. But a one sample test, a lot of times, if you double that probability, you would find the two sample here, right? If it's a less than, and it is less than, right? Okay. Let's see, last thing, I think. Oh no, degrees of freedom and then chi-square contributions. Degrees of freedom for a one sample t-test is just n minus 1. Degrees of freedom we need to show, always show, right? Degrees of freedom equals blah. If you're running a confidence interval or a fat pi kind of test. Okay, so if you're doing any kind of inference, show your degrees of freedom. The only time we don't do it is one prop Z or two prop Z. Okay, so any Z test. So Z test we don't. Everything else you've got to have degrees of freedom. So one sample is n minus 1. Two sample, your calculator will calculate. If you have to do it by hand, which you won't, smaller of sample size 1 minus 1, sample size 2 minus 1. Okay, whichever is smaller. But your calc will do. Just report it at the end. So your calculator say degrees of freedom equals 27.599. Write that down. Okay. Paired t-test is just the number of differences minus 1. Okay. Linear regression, slope, it's bivariate data. Bivariate means 2. So it's going to be n minus 2. Chi-square goodness of fit, categories minus 1. Chi-square independence homogeneity is rows minus 1 times columns minus 1. Okay. Last thing, chi-square contributions. Now, when you do GOF, they show, right? If you run a GOF test or goodness of fit test, it will show the contributions. It won't for homogeneity. So this is for homogeneity or independence. You have to figure it out yourself. Chi-square contribution for all of the tests is observed minus expected squared over expected. So I have to calculate that. I always have the observed. The observes are right here, right? So finding the expected. Okay, to find expected, we're going to take the row total times the column total and divide it by the total. Okay, so for in this case, if I want to find the contribution here, this is the observed. If I want to find the expected here, okay, I would find this total, which is 40, and I would multiply it by this, which is 30. So 40 times 30 divided by the total, which I think was 40 and 50, was it 90? I think the total was 90. Okay, and that's going to be my expected, and that goes into the expected there. My observed would go there, and I would find the contribution for that one. Your calculator does this. You could enter this all into matrix A, run your chi-square test, then look at matrix B, and you could find that as well. Okay, this is probably faster, especially if they gave you the totals already, but feel free to use your matrix as well. And that's it. That's it, people. Thank you. I think we're good. Yeah. Yeah. All right. That's it. Good luck, y'all.